Let's have a look at our homework from last night, page 708, dealing with photons. If you remember, up until yesterday, when we talked about light, we were referring to light as a wave. The properties of waves that are exhibited by light, or EMR, remember refraction, diffraction, interference, polarization, those are all still valid. We still believe that light is a wave, but now, post-Einstein 1905, we now believe that light is also a particle. We say that it has a wave-particle duality associated with it. And as I said yesterday here, over the next few days, we're going to be looking at the particle nature of light. We're not discounting the wave nature. We're not throwing that away. We're just not focusing on that over the next couple of days. We're focusing now on the particle nature of light. Einstein said that energy exists as a particle. A photon, which is a quantum of energy. And the energy that a photon has would be equal to h times f, or hc over lambda. H being a constant that we call Planck's constant. Two values, but with two different units. In question number 1 here, for our homework, we want to find out how much energy is delivered by 1,000 of these photons. Now, if you look in your textbook, and I know that some people did, they're going to find an equation that says this. E is equal to n times h times f. I don't like that equation. And the Alberta Diploma Exam people don't like that equation either, clearly because they didn't put it on your data sheet. I'm glad they didn't put it on your data sheet, because I think that takes away from the understanding of what's going on. This n would be a number. Okay, 1, 2, 3. If there's 5 photons, then n would be equal to 5. But to me, in a question like this, we're better off understanding what's going on, calculating the energy of one photon using hc over lambda, and then saying, okay, wait, we have 1,000 of them, so let's just multiply the energy from 1 by 1,000. So let's do that. Let's say h is, our answer is in joules here, so I'm going to use 6.63 times 10 to the minus 34 joule seconds times the speed of light, 3 times 10 to the 8. And I'm going to divide that by the wavelength here, which is 400 times 10 to the minus 9. Be careful here. I don't know how often I see this. This is 400 nanometers, and a nanometer is 10 to the minus 9. Don't say 4 times 10 to the minus 9. That's not right. Okay, 4 times 10 to the minus 9 is not right. It's 400 times 10 to the minus 9. Now, you could say 4 times 10 to the minus 7. Okay, that would be correct. But I think it's easier just to leave it as 400 and replace the nano with 10 to the minus 9. All right, when we do this, what do we end up getting here? Let's calculate this. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 400 times 10 to the minus 9 gives us an energy for one photon of 4.9725 times 10 to the minus 19. Okay, there we go. That's almost our answer, right? We have 1,000 photons. If this is the energy for one photon, how are you going to find the energy for 1,000? Times it by 1,000. What do you end up getting? 4.97 times 10 to the negative 16. There we go. Done deal. Question number 2 says, how many 400 nanometer blue light photons per second are required to deliver 10 watts of power? 10 watts is power, right? We know that the power that we have is 10 watts or 10 joules per second. We're looking for, what are we looking for here? The number of photons. The number of photons in 1 second. So let's make my time interval 1 second. The number of photons per second. The wavelength of my light is 400 nanometers, or 400 times 10 to the minus 9 meters. We know this now. When we're looking for a number of something, it's total over the amount for one. The number of photons will be the total energy divided by the energy of one photon. The energy for one photon can be found by hc over lambda. So let's do that. Let's say 6.63 times 10 to the minus 34 times 3 times 10 to the 8. And let's divide that by the wavelength of 400 times 10 to the minus 9. Okay, that gives us the energy of a single photon, which is same thing as we had in the last one, right? 4.9725 times 10 to the minus 19. Okay, there's the energy for one photon. Now, how do we get the total energy? What do we have given to us here? Power and time. Isn't power work over time or energy over time? 10 watts times 1 second equals 10 joules. All right, so let's say it's 10 joules divided by 4.9725 times 10 to the minus 19 joules. Divide those two numbers and we should get 2.0 times 10 to the negative 10 to the positive 19. Right? How many people got that? Okay. All right, yesterday we did a little demonstration to help us to illustrate a little bit the photoelectric effect, which, as we know, the photoelectric effect discovered in 1887 wasn't correctly explained for another 18 years. Lots of ideas as to what caused the observations that were made for 18 years, but no explanations that would work for the observations. The observations that essentially said, basically said, when light strikes a metal, sometimes electron or electrons are ejected. So sometimes the metal becomes charged positively because it loses negative charge, it loses electrons when light strikes it. Hertz correctly reasoned that if an electron was being ejected, it's because the light gave it energy to do that. That's correct. Hertz also correctly reasoned that if an electron wasn't being ejected and you wanted it to be ejected, then you needed more energy. Light strikes a metal. Hertz was correct in how it was ejected, and he was kind of correct in how you could get it ejected if it wasn't being ejected already. You need more energy. But Hertz's explanation as to where the energy came from was wrong. He said, if it's not happening, you need more energy. Where do you get more energy? What did Hertz say? Remember the demonstration we did yesterday? You add more light, right? You get more light. You either shine brighter light or you shine it for longer, whatever, you get more light. But that didn't work. It didn't matter how much we shone on it. If a particular type of light didn't work, it didn't matter how bright it was or how long we shone it on it, the surface for, it didn't matter. Electrons wouldn't be ejected. So along comes Einstein with his little nifty photon theory, which says, oh, look, here's why that doesn't work. Energy is not related to the amount of light that you have. Energy is related to the type of light, the frequency of light that you have. If you've got electrons not being ejected and you want them to be ejected, yeah, Hertz, you're right, you need more energy. But you don't get that from more light, you get that from more frequency. So don't jack up the intensity of the light if it's not causing electrons to be ejected. You want to jack up the frequency of the light. You want to go from infrared to visible light, or you want to go from visible light to ultraviolet to cause electrons to be ejected, because that's what gives you more energy. You want photoemission? Photoemission means the ejection of electrons. You need more energy. You get more energy from higher frequencies. Remember yesterday the demonstration when we throw the paper, one piece of paper, nothing happened. 25 pieces of paper, nothing happened. We pretended to throw the calculator, what happens? An electron is ejected. A single photon causes it as long as it's more energetic. And it's more energetic because it's a different type, a higher frequency. So Einstein said that since light is a particle whose energy is related to the frequency, higher frequency EMR was more likely to cause emission than lower frequency EMR. Now, yesterday when we were doing our little demonstration, we alluded to this term that I'm about to define for you right now. We call it the threshold frequency. If light is not causing electrons to be ejected, and you want electrons to be ejected, then you need to increase the frequency. That that insinuates that there's got to be a minimum frequency at which electrons will become ejected. You're below that frequency, nothing happens. You're above that frequency, something happens. We call that frequency the threshold frequency. The symbol for threshold frequency is F subscript 0. It is the minimum EMR frequency at which electrons will be ejected. So we would say that if the frequency of the EMR is below the threshold frequency, nothing happens. If the frequency of the EMR is at or above the threshold frequency, something happens. Electrons are ejected. F would stand for the frequency of the EMR. F0 would stand for the threshold frequency, that number that's unique to each different metal that we have to exceed in order to cause the electrons to be ejected. Another term, the work function, which kind of goes along with threshold frequency. Symbol for that is W. The work function is the minimum EMR energy. At which electrons will be ejected. Now, in the process of ejecting electrons, you end up using up energy as well, and the energy that gets used up corresponds to the work function. So I'm going to put in brackets here kind of a second definition for work function. It is the minimum energy necessary to eject the electrons, but it's also the energy used up in the process. We know that energy is equal to H times F. Minimum energy, look, if energy is HF, or HC over lambda, then minimum energy, W, would be H times minimum frequency, HF or HF0. It would also be equal to HC over lambda, what's that going to be? Lambda minimum frequency. Anybody want to take a stab at that? Why is it maximum wavelength? HC over lambda max. As frequency goes down, wavelength goes up. You need to be above a certain frequency, but you need to be below a certain wavelength, because frequency and wavelength are inversely related to each other. So here's my equation that I learned here yesterday. That's anytime you have a photon, whether it's a photoelectric effect or otherwise, you can use this. Now we have one that's unique to the photoelectric effect. Work function, minimum energy necessary to eject an electron is equal to Planck's constant times the minimum frequency necessary to eject the electron, or HC over lambda maximum wavelength necessary to eject the electron. So just like if the frequency is less than the threshold frequency, nothing happens. If the frequency is greater than the threshold frequency, something happens, electrons are ejected. We could also say if the energy of the photon is less than the work function, nothing happens. If the energy of the photon is equal or greater to the work function, then something happens. The electron or electrons are ejected. Bless you. This is essentially what we just said, right? Photons below the threshold frequency will cause no electrons to be ejected. Photons above the threshold frequency will cause the electrons to be ejected. Now, remember, I wrote this down already. I'm going to say it again though. F less than F0, nothing happens. F greater than or equal to F0, something happens. Electrons are ejected. Now, if no electrons are ejected, it doesn't matter what you do. If you're above the threshold frequency and electrons are ejected, understand that it's a 1-to-1 ratio. So that if you have 1 photon, it causes 1 electron to be ejected. If you have 28 photons, it causes 28 electrons to be ejected. Yesterday, when we threw 1 piece of paper at our piece of metal, at Ollie, hey, then nothing happened. 25 pieces of paper, nothing happened. We pretended to throw a calculator at him, we would have gotten a single ouch. We pretend to throw 25 calculators at him, we get 25 ouches. Right? It's a 1-to-1 ratio if and only if you're above the threshold frequency. Now, when electrons are ejected, in other words, when you're above the threshold frequency, higher frequencies still makes them more energetic electrons. So it's still a 1-to-1 ratio. 1 photon will still cause 1 electron, but if you're way above, barely above the threshold frequency, 1-to-1 ratio, electrons are ejected. Way above the threshold frequency, 1-to-1 ratio, but the electrons that are ejected aren't just barely ejected, they're like ejected big time with lots of energy, with higher energy. So let's say if F is bigger, like a lot bigger than the threshold frequency, yeah, it's a 1-to-1 ratio, but the electrons will be more energetic. And logically, as long as we accept Einstein's photon theory that E is related to H times F, then logically that should make sense to us. If you have a photon with a whole lot of energy, then you can have, and it causes an electron to be ejected, then that electron can have a whole lot of energy because it's got way more available to it to be transferred to it. Peter? Yeah, I'm sorry, is it what? Yes, they are. Guys, if you didn't hear that, Peter just asked, is it just light that's photons? Or can radio waves and microwaves and so on be photons as well? The answer is yes and yes. Just light can be photons because when I say light, I mean EMR. Okay, not just visible light, but all types of EMR. So that means radio waves and microwaves are photons as well. But understand that it would be almost impossible. You'd have to have such a ridiculously low threshold frequencies for microwaves to cause the photoelectric effect. It wouldn't happen. But they are photons, the same as visible light. It's just they're too low a frequency to make this happen. Below the threshold frequency, increase the frequency all you want. As long as you stay below, nothing's going to happen. Increase the number of photons all you want. Doesn't matter. Nothing's going to happen if you're below the threshold frequency. But go above, it's a 1-to-1 ratio. 1 photon causes 1 electron. 25 photons causes 25 electrons. Way above, 1 photon, 1 electron, 25 photons, 25 electrons. But those 25 electrons are more energetic than if the photon was just barely above the threshold frequency. Oh man, it keeps going. Stopping potential. Stopping potential, well, this is the potential difference. You guys know what potential difference is, right? Delta V. By the way, the symbol for this would be V stop. The potential difference required to stop an already ejected electron. Now, that's not going to make a lot of sense to you until I explain it. This isn't really a photoelectric effect thing per se, because it's assuming the electron has already been ejected. The photoelectric effect has already taken place. You guys know from back in Unit 2 in your electricity unit, you guys know that as an electron experiences a potential difference, it can cause that electron to either speed up or slow down. It would be like the car going down the hill or the car going up the hill. Depends upon which way the potential difference is oriented. When an electron is ejected, we sometimes apply a potential difference to slow it down and stop it. Now, why would we do that? Well, because sometimes we might want to measure properties of the electron so that we can determine the work function or the threshold frequency of the metal. We may want to do an experiment to determine what the threshold frequency of the metal is, and therefore we may need to stop the electron in order to do it. Tomorrow, that'll become a little bit more clear. You're designing a solar-powered calculator, a calculator with a solar cell on it, right? Or better yet, you want to power your house by solar electricity, solar-powered house. But you want to design your own solar cell. You don't want to go buy one of those ones on the internet because you don't trust the people that are selling these things on Amazon. So you want to design your own. You got to come up with a metal that's going to have a threshold frequency in the range of visible light. You don't want to have a metal that has a threshold frequency in the range of X-rays, because it's not going to work very well out in the sunlight. It's got to be in the range of visible light. So you have to do an experiment to determine what the threshold frequency of all these different metals are. Well, you test these metals, you get electrons ejected from them with a high frequency photon, and then you stop the electrons once they've been ejected with this potential difference. And again, tomorrow you'll see how that would lead to the determination of the threshold frequency. Yep. I don't know what you're talking about.
You said like 2 days ago, you were like, we're going to watch a video and everything.
Finally, conservation of energy. What do we mean by this? Well, energy can't be created or it can't be destroyed. It can be transformed from one type to the other. It can be transferred from one thing to another. Sorry, before I give you this, I wanted to give you an equation for this. Stopping potential. You guys know that if the electron has kinetic energy, then that kinetic energy ends up being transformed into potential energy as it slows down, right? Like a car going up a hill, it has kinetic energy at the bottom, gets transformed into potential energy when it goes to the top. We would say here that kinetic energy that the electron has, 1/2 mv squared, ends up being converted to potential energy as it slows down and stops. Now, Ek is 1/2 mv squared, so I'm going to actually say that Ek max, the max kinetic energy of the electron that's been ejected, is 1/2 mv squared, but it also corresponds to Q times the stopping voltage. Because as the electron stops, the kinetic energy is converted to potential. Now, finally, this conservation of energy thing. We say EI equals EF for conservation of energy. We did that a bunch of times back in Physics 20. What kind of energy do we have at the beginning of a photoelectric effect problem? When light strikes a metal, electron ejected, what kind of energy do we start with? Yep. No. When light strikes a metal and the electrons are still in the metal, what kind of energy do we start off with? Kind of a potential, I suppose. It's not the term I'm looking for, though. Peter, it looks like you're ready to give me an answer. The photon energy, the light energy, we're going to say HF. So this is what we start with. That would be EI. What kind of energy do we end up with? Ethan, you know the answer to this one. What kind of energy do we end up with after the electron's been ejected? Kinetic energy. But here's the problem. The electron doesn't have as much kinetic energy as the photon had potential. We lose a little bit of energy. So what we end up with, plus the energy that we lose, ends up being equal to what we start with. Does that make sense? What's it called? The energy that we lose. The energy that's used up in the process of ejecting an electron. No. The work function. So we're going to say HF is equal to 1/2 mv squared, or sometimes we just write an Ek max, because we know that's 1/2 mv squared, right? Plus the work function. What we start with is equal to what we end up with plus whatever we used up in the process. So let's look back at the equations we have. Okay, this is the big one, which doesn't appear on your data sheet, by the way. This one that I have circled in red doesn't appear on our data sheet. This does. E is equal to HF equals HC over lambda does, and then W is equal to HF0 does appear on our data sheet as well. 4 equations here now that we have available to us with the photoelectric effect. Just a quick little piece of strategy. First of all, remember this one. Why? Because it's not on your data sheet, and because you're going to use it a lot. It's probably the most commonly used equation with the photoelectric effect, and sadly, it's the one that doesn't appear on our data sheet. I don't know. They used to put it on the data sheet, and then they took it off one year. About 10 years ago, they took it off. Maybe they took it off because they figure that knowing that it's conservation of energy, you can figure it out. I don't know. Same rationale would apply to a whole bunch of other equations too, though. So I don't know. Yep.
Why does the F always like change? It seems to change.
I'm not sure what you mean there. Let's try an example on page 716 here. It says blue light shines on the metal surface shown in figure 14.13. We don't really care about the diagram. It causes the photoemission of electrons. Electrons are ejected. So first of all, what do we know about blue light? If it caused the electrons to be ejected, what do we know about blue light? It is above the threshold frequency, right? The minimum necessary frequency must be somewhere below blue. Blue is above the threshold frequency because it's causing electrons to be ejected. So a stopping potential or a stopping voltage of 2.6 volts is required to stop electrons, then determine the maximum kinetic energy of the electrons. What do we got here? We've got V stop is 2.6 volts. It looks like all we've got. We're looking for EK max, the max kinetic energy of the electrons. What do you want to do here? We got E is equal to HF equals HC over lambda. We've got W is equal to HF0 equals HC over lambda max. We've got EK max equals 1/2 MV max squared equals QV stop. And we've got HF is equal to EK max plus the work function. Yeah, Ollie?
I would like to try the EKM equals 1/2
Sure.
equals QV stop.
So let's try EK is equal to QV stop. EK is equal to QV stop. We know what, hey, what's Q? What's being ejected here? It's an electron, so let's use the charge of an electron. When you're doing a photoelectric effect problem, it'll always be the charge of an electron. Times that by the stopping voltage or stopping potential, 2.6 volts, and what do we end up with? We're going to say 1.6 times 10 to the minus 19 times 2.6 gives me a kinetic energy of 4.16 times 10 to the minus 19. 4.2 times 10 to the minus 19. And that would be joules. Joules, because we're using standard units. When we use standard units, we get standard units. By the way, remember I said you can almost always use whichever one you want? As soon as you introduce 1/2 MV squared or QV stop, you got to use joules. Anything else, use whatever's convenient. But as soon as you're using 1/2 MV squared or QV, it's got to be joules. No other way around it. So we know when we use QV stop here, we're going to get joules out of it. We could convert that to electron volts, but we know we get joules out of it. Okay, I want to do one more example problem, and then I'm going to leave you with a couple questions for homework here that are going to go pretty quickly for you, and then a couple questions with this. One more example for you here on page 718. Experiments show that the work function for cesium is 2.1. For some other metal, it could be different, right? It will be different. For cesium, it's 2.1. It's the threshold frequency and the threshold wavelength, or we're looking for F min and lambda max, the threshold frequency, threshold wavelength. Here's our equations that we use again with the photoelectric effect. What do you want to try here? Probably this one, right? W is equal to H times F0. Okay, we've got a work function in electron volts. Can we do that? Sure we can. The only time right now that we can't do that is if we're using 1/2 mv squared or QV stop. We're not doing that here, so we're allowed to use the electron volts. Let's stick with it rather than converting. But make sure you use the 4.14 value for the electron volt seconds for Planck's constant. So 2.1 divided by 4.14 times 10 to the negative 15. 5.07. Anything below that frequency, nothing happens. Anything above that frequency, 1 photon causes 1 electron. By the way, could you have converted that to joules and then use 6.63? Sure, you can always use joules, but you can usually use the electron volts as well if it's convenient. Okay, let's say W is equal to HC over lambda max. Lambda max is the threshold wavelength. So it's going to be HC over W. When we get that value in meters, it's the maximum. So anything above that wavelength, nothing happens. Anything below, something happens. Below the frequency, below this frequency, nothing happens. Above this wavelength, nothing happens. All right, your homework tonight is, besides your assignment that isn't due till Monday, your homework today is the practice problems that go along with both of those examples, page 716 and page 718. And I think it's about 5 questions that should go fairly quickly for you.